Ever wondered why we don't fly off the planet, or why it's harder to push a heavy object than a light one? These questions have answers rooted in Newton's laws of motion. These three laws form the bedrock of classical physics, a framework that helps us understand the universe and its workings. Every day, in every moment, these laws are at play. From the simple act of walking, where your foot pushes against the ground and the ground pushes back, to the flight of a bird adjusting its wings to the air resistance. Even the very act of breathing, where air pressure differences allow for the exchange of oxygen and carbon dioxide, is governed by these laws. They also extend beyond our immediate surroundings, influencing the orbits of planets and even the expansion of the universe itself. So, buckle up as we delve into the fascinating world of Newton's laws of motion. Newton's first law, often called the law of inertia, states that an object at rest stays at rest and an object in motion stays in motion. This might sound complex, but let's break it down in simpler terms. Imagine a book lying on a table. It's not moving, it's not jumping up and down or sliding to the left or right. It's simply resting, and it's going to stay that way unless something happens to change its state. This could be a gust of wind, a push from your hand, or even an earthquake shaking the table. Until one of these things happens, the book is quite content to stay exactly where it is. This is the first part of Newton's first law, or the law of inertia. Now let's consider a different scenario. Suppose you're playing football and you've just kicked the ball. It's rolling across the field, moving with the force of your kick. According to Newton's first law, that ball is going to keep moving in the same direction and at the same speed unless something happens to change its state of motion. This could be another player stopping the ball, a gust of wind blowing it off course, or the friction from the grass gradually slowing it down. In both of these examples, the book on the table and the ball on the field, the objects want to keep doing what they're doing. They want to keep resting or keep moving until something makes them do otherwise. This is inertia, the natural tendency of an object to resist changes in its state of motion. So next time you see a ball rolling on the ground or a book sitting on a table, remember Newton's first law. Remember that these objects are not just passive entities, but active participants in the physical world, each with their own inertia, their own resistance to change. In essence, the first law tells us that objects resist changes in their state of motion. The second law of motion shows us the relationship between force, mass, and acceleration. It's a simple concept, but it's also one of the most fundamental in physics. Now, let's try to break it down into something we can all grasp easily. Imagine you're trying to push a heavy boulder. You put all your strength into it, but it barely budges. Now, imagine a small pebble. With the same amount of force, the pebble zooms away. This is the essence of the second law of motion. The heavier the object, the more force you need to move it. The lighter the object, the less force you need. But there's more to it. Remember that force isn't just about making things move. It's also about changing how things move. Let's consider a car as an example. A more powerful engine doesn't just make the car go faster, it also makes it accelerate faster. That's the force at work. Now let's take this a step further. We've talked about how force affects movement. But how does acceleration fit into this picture? Well, acceleration is simply the rate at which an object changes its velocity. So, if you push a shopping cart in a supermarket and it starts moving, that's acceleration. If you push it harder and it moves faster, that's even more acceleration. So, when we look at Newton's second law, what we're really seeing is a description of how force affects acceleration. Push harder and the object accelerates more. Push less and it accelerates less. It's a direct proportional relationship. But there's a twist. The mass of the object also plays a role. The heavier the object, the less it accelerates for a given force. That's why it's harder to push a full shopping cart than an empty one. The mass is acting as a kind of resistance to the force you're applying. Simply put, the second law explains how the velocity of an object changes when it is subjected to an external force. Newton's third law, often summarized as every action has an equal and opposite reaction, might be the most famous of them all. This principle is so ubiquitous in our lives that it's easy to overlook its profound implications, but let's try to understand it a bit better. Imagine you're on a boat, enjoying the tranquility of the lake, and you decide to take a leap into the water. As you jump off, the boat moves backward. Now, you didn't push the boat, yet it moved. This is Newton's third law in action. When you jumped off, your action exerted a force on the boat, and in response, the boat exerted an equal force in the opposite direction, hence moving backward. Let's consider another example, something a bit more dramatic. Firing a gun. When a gun is fired, the bullet is expelled forward with a great force. However, the shooter also experiences a kick or recoil in the opposite direction. This is because the force exerted on the bullet also creates an equal and opposite force on the gun, causing it to jerk backward. This law isn't just about physical actions and reactions though. It applies to forces too. If you've ever played tug of war, you'll know that the harder you pull the rope, the harder the other team pulls back. That's because the force you apply is met with an equal force in the opposite direction. And it's not just in games or dramatic scenarios. Newton's third law is at play in our everyday life. From the propulsion of a rocket to the simple act of walking, where the force we apply on the ground propels us forward, this law is constantly in action. It's fascinating, isn't it? How a law formulated centuries ago by Sir Isaac Newton still holds true and shapes our understanding of the world and the universe. The third law reminds us that forces always come in pairs. If you push on something, it pushes back with equal force. This is the symphony of forces that choreographs the dance of the cosmos. Now that we've journeyed through each of Newton's laws of motion, let's bring it all together. Let's start by going back to Newton's first law, the law of inertia. This law tells us that an object will keep doing what it's doing until a force acts upon it. So when you're in a car and it suddenly stops, your body wants to continue moving forward. It's inertia at work. And seatbelts are there to provide the force needed to stop us from flying forward. Then comes Newton's second law, which brings in the concept of force and acceleration. This law states that the acceleration of an object is directly proportional to the net force acting on it, and inversely proportional to its mass. In simpler terms, if you push a light object, it moves faster than a heavy object. This is why it's easier to push a shopping cart than a car. Last but not least, Newton's third law tells us that every action has an equal and opposite reaction. This law explains why you recoil backward when you fire a gun, or why a swimmer propels forward when they push the water backward. These three laws, taken together, govern virtually every physical event around us. They're the reason why we can predict the trajectory of a thrown ball, why planets orbit the sun, and why we don't float off into space when we jump. In our daily lives, we may not consciously think about these laws, but we experience them in countless ways. Every time you push a shopping cart, you're applying a force that results in acceleration, thanks to Newton's second law. When you're walking, you push the ground backward, action, and in response, the ground pushes you forward, reaction, illustrating Newton's third law. Even in sports, these laws are at play. When a footballer kicks a ball, the force they apply, combined with the mass of the ball, determines how fast and far the ball will go, a perfect example of the second law, and the ball continues to move until an external force, like gravity or friction, slows it down, demonstrating the first law. Similarly, in space exploration, Newton's laws are fundamental. They help scientists calculate how much force is needed to launch rockets into space and keep satellites in orbit. The power of Newton's laws isn't just in understanding the physical world around us, but also in predicting how objects will behave under different conditions. This predictability is crucial in fields like engineering, architecture, and even video game design, where understanding how objects move and interact is essential. In conclusion, Newton's laws of motion are not just scientific theories, but principles that underpin our daily experiences and the functioning of the world as we know it. They are fundamental to our understanding of the universe and continue to shape scientific and technological advancements. Remember, each time you push a door open, catch a ball, or even just take a step forward, you're witnessing Newton's laws of motion in action.